Hello everyone and welcome to Chapter 4 of OpenCV+Skyblock. Today we'll be going over the largest block of them all, how to automate Dwarven mines. First things first, a huge disclaimer. This bot demands constant human attention. There are many unresolvable circumstances that arise from game mechanics which are too complex for a bot to solve. For example, when farming in Hypixel Garden, one cannot expect an AI bot, as of now, to catch pests on its own. Hence, I am not responsible if you fail the macro check like Tesla drivers who watch anime while using FSD. Again, this is only to automate the mining part. Special events like Golden Goblins, Mithril Guchmon are not included in this automation. To understand the program, we first have to understand how coordinates work in Minecraft. Minecraft blocks like this one are indexed by their lower left corner. So for example, if I stand on top of this block right here, see my coordinates in the upper right corner says that I am approximately at 030. However, the upper left corner says the targeted block is located at 020. One other thing is that when we say we look at a block, we are not looking at its center. We are looking at the face of it. For example, if I want to mine that redstone block, I do not look at its center like this. That way, I can only mine the iron block, which I do not want. I have to look at its face, facing the positive y direction, and mine it like that. So knowing all that, how do we make it happen? Well, it's simple. Some 3D geometry math. Now let us start with the header file. First are the includes. Nothing out of the ordinary. So let us start with the class itself. First, we define a structure for storing information about one block. First is the block position, stored as a .3D object. The 3D means that this is an integer object. Next is the name, which actually stores the block type. Next one is a steady clock time point, named last broke. This is because in the Dwarven mines, when mithril blocks are mined, they turn into bedrock, and after a while, they turn back. This time point stores when the blocks are last broken or last mined by the player. Next is an unsigned 64-bit integer named hashPos. This is obtained by hashing the position of the block. Finally is a Boolean array named faces. This stores which faces of the cube are exposed to the outside world. The order is positive x, positive y, positive z, and negative z. Next is an array of strings storing the name of the mining areas. They are lava springs, royal mines, upper mines, ramparts quarry, and cliffside veins. Following is a .3D array to store the positions the player must stand at in each area to mine. Finally is a function to calculate the hashed position, as shown in the struct. These three are all used by the main function outside the class. Next are the private variables. Firstly is the string array mithril. This stores the vanilla name of the useful blocks: dark prismarine, cyan terracotta, prismarine, gray wool, and prismarine bricks. Next is an array face direct that stores the relative coordinates of the center of each face in accordance to the lower left corner at which the block is indexed. For example, if we want to see where the center of the positive x face is, then we need to add 1 to the x position, add 0.5 to the y position, and add 0.5 to the z direction. Next is a string named faces. This just stores the name of the coordinate axis. The camera height is the distance from the feet of the player to the actual camera starting point. Because in Minecraft, we are not a camera looking at the ground where the player position is displayed. We are a standing person. The next is the corner dist constant. This is just used to identify the points that are actually on the block. The value 0.866 is obtained by adding 0.5 squared 3 times and taking the square root. Next is an unordered map to store the block structs declared in the previous section. Also an mouse input object and a point2f which stores the set yaw pitch. Next are the pause controller and MC screenshot classes that are passed by reference. Now begins the math part. As demonstrated here, yaw and pitch are simply spherical coordinates. For those that don't know, spherical coordinates are described by a distance, which is non-existent here, measured from a certain axis, this angle called theta, which corresponds to yaw, and another angle called gamma, which corresponds to pitch. This is the system that Minecraft uses to describe its camera angles. To acquire the line of vision in 3D, we need a function to transform it from simple yaw and pitch data into a 3D vector. So here it takes a point2f object and transforms it. Firstly, it converts the angles from degrees to radians, hence by pi over 180. Next, the direction x is simply sine of yaw times cosine of pitch, and the direction y is simply sine of pitch. Direction z is cosine of yaw times cosine of pitch. Finally, it returns the result. In 3D, a line is given by this form: a starting 3D point and a direction that describes an infinite line multiplied by a random t. So the next thing we need to ask is, at what point on the line, at what coordinate will the line of vision intersect a surface? That is what this function is used for. It takes a point3f line vector object, a position object, a critical variable value, and an axis selection. The switch is just to handle all 3 axes in one single function. So we will look at only the first case. The value of t is calculated by the difference between the critical position and the current position divided by the line vector of x. Next, the point is calculated by the critical position. For y, it is position of y plus t times line vector component y. And position z is likewise. With all of that, we can now ascertain which face the viewer is looking at. So firstly, we need to find every point that the line intersects the cube's planes, which means that we will get 6 points. That includes points like these, which are outside of the cube's faces, but intersect the face's plane. And also these dotted points, which are on the cube's surfaces. Next, we need to know which point is closest to the viewer. Originally, I only took one step, which is to find the points and see which is closest to the center of the cube. However, that is not the case. We need to see which dotted point is closest to the viewer. That way, we can ascertain that this face is the one the viewer is seeing. That is exactly what the find face function does. It takes a point3f block position, a point3f player position, and a point2f yaw pitch source. First, it shifts the player position to the camera viewpoint by adding camera height to the y coordinate. Next, it initiates some selection variables. Then it calculates the critical data. It gets the vector of the line from the function, the center of the block from point3f by just applying some basic addition. And also it initiates an array of face points, since some of the points' coordinates will have to be used twice. Finally, it initiates a Boolean variable called selectFace. This stores which faces are selected in the first step. Next, it iterates through each face. For each one, it calculates the point at which the view line intersects with the plane, as we can see here. Common to all, it calculates the distance from the point at which the line intersects the face and the center. If the distance is smaller than current distance, then select face is set to true, else it is set to false. That is the first round of point selection. The second round looks at only the points that are in the first round, hence this if clause. It calculates the distance from the face point to the player position and selects the one with the minimum distance. This is just in case of errors, but it has never been triggered. Finally, it returns the face. With the basic geometry established, we can now work to memorize the block and spatial positions. So here I am in the Dwarven mines, ignoring the Mithril that is going on. We need to memorize the block, because let's suppose we just use pick a bolus. And now we're facing an entire wall of bedrock and some titanium, because I have the titanium thing. So you need to remember that there is this mithril block right here that you can mine. And that is why we cannot use the pinhole camera model to see which blocks are available to mine, because the camera can't see outside the camera. To store information about the blocks, I have chosen the TXT file format, because raw text is the easiest way to store information. Here is the structure of each line. The block and end block are keywords that signal the start and end of each block's information. First is the block coordinates, separated by commas. Next is a colon signaling the start of the block name, right here, and another colon signaling the end of the block name. 6 ones or zeros signaling which faces of the block are available. Finally, another colon. The text file was generated by this function called saveWorld. The integer choice signals which area of the mines is being saved. Here, it opens the file, and since its output, if there is no such file, it will create one. Using this for loop, it iterates through each block stored inside the world map, and for each block, it outputs the starting keyword block, then the position separated by commas, next a colon followed by the block name, and another colon. Next, it outputs which faces are available. Finally, for each line, it outputs the end block keyword. And finally, it closes the output file to prevent memory leaks. To load the block information from the file, we have this function called loadWorld. Again, the choice integer indicates which area is being loaded. It opens the file, and this time we need to test if there is such a file. In the while loop, it reads a line, and if the line is empty, it means the file is finished and all blocks have been loaded. Hence, it breaks out of the loop. Next, see if the line has the correct keywords. If there isn't, then output another error message. Next, it finds the commas and colons that separate the information. It extracts the coordinates into individual strings, the name into a separate string, and the available faces into another string. Next, it declares a temporary block, initializing it with the string information already collected. It calculates the hashed position by using the function. For every face, it inputs the information by comparing the ith character in the faces string to 1. Finally, it sets the last block to null, and it inserts the block into world. And lastly, it closes the file to prevent memory leaks. To remember the area, we need a function, and that is what the log area function does. It also takes an integer signaling which area it is logging. So it first loads the world. This is because it is appending and changing the information. For example, if we look at a block at a new angle and find a new face, then the program needs to update that information. If the program finds a new block, then we need to add that information. So while the user does not stop the program, it waits for them to change to Minecraft with a wait if paused. Next, it uses the MC screenshot class to get all of the information. First, it checks if it is a valid block. If the block name is not error, or titanium, or bedrock, then it proceeds to add the block. Of course, outside this if block, it only gets the block name. Only here does it convert to yaw pitch, player pause, block pause. Next, it gets the viewing line. Before logging, it outputs a message. It finds which face of the block the player is looking at. Next, it initiates a temporary block with a position and the name, and gets the hash pass of the block. Finally, it outputs the face that the player is looking at, and sets the face to true. We do not use a for loop here because at one point, the player can only look at one face. If the block already exists, update the data. Otherwise, insert the block. So that is what it is doing here. If world.find temp hash pass is not equal to world in, then it proceeds to update the data. Otherwise, it inserts. And that is all for the log area. Now that we have the world stored and we have identified faces, we need to next find which face to look at while mining a block. And that is what the cal yaw pitch function is for. It takes a player position by reference and a block target. It first offsets the camera height. Next, it initiates some variables to find the exact face. Because there are multiple faces that a block can be stared at, in some cases, it needs to find the closest face to the player. And that is what this for loop is doing. Firstly, if the face is not available, because it iterates from 0 to 5, it continues, just ignores it. Next, it calculates the center point of the face and calculate the distance from the face point to the player. If the distance is smaller than the current minimum distance, then it updates the variables. If there is no face selected, then outputs an error message. And I never got to this part because this never happened. Next, it finds the vector from the player viewing point to the block face. And it converts that to spherical angles, as we discussed earlier. The next part is to invert the yaw and pitch. The vector of a line only describes the direction that it is facing. However, it can be in both ways. For example, take this vector -1, -1, -1. It can both mean that the player is going upwards or that the player is going downwards along the line. So we use the player position relative to the block position to invert the yaw and pitch. Note that at this point, yaw is still in radians, so we add pi instead of 180. Finally, we convert the radians into degrees and return the results. To make everything move, these functions are carried over from the farming section. Move mouse, change set yaw pitch, left click, reset yaw pitch, mouse down and mouse up. Also, the maintain yaw pitch function, which is run in a separate thread. Before we proceed to the actual mining function, we need to mention this. This selects a random block from the world, which is an unordered map. It is in the form of an iterator. Originally, I wrote a complex logic to find the next block, It first considers all the 18 blocks that could be next to the original block, and then selects the right one by random. However, when I did the pointing test, I found this method to be quicker. Finally, we come to the mining function. To start, it loads the world, and after loading the world, it resets the last broke time point of each block to the current time. Now the main mining loop. While the user does not stop the program, it first waits for the user to switch to Minecraft, then press delete to enable the function. And for each one, it takes a random block and stores it inside here. Next, it checks if the time point inside the block is bigger than 5 seconds from now. If it is not, then just continue to the next one. Next, we need to move the mouse to point at the block, more specifically at a face of the block. So we need the player position, and we get that from the MC screenshot class. And we calculate the yaw and pitch of the block that is needed. Then we set the yaw pitch to the target. Next, we request not allow to give time for the mouse to move to the target. Finally, we mine the block. First, we click the mouse down, and for each round, we get the name from MC screenshot. While it is not equal to bedrock, we continue. If the mined block turns into titanium, then we need to lift the mouse and then click again. However, this needs to only occur once, and that is where the Boolean variable last title comes in. Finally, since this is the longest time the program spends, we execute the pause here. After mining, it lifts the mouse, gives the signal, and updates the time point inside the world. After mining has ended, it just outputs a message and returns. Lastly is the pointing test function. This is just a function I use to debug. It iterates through the entire world and points at each block in sequence. It does not mine the block, it just points at it. This is also the time when I discovered that a randomized order is better than the complex sequence selection. Just like in farming, we have a main function for mining. It first asks the user to select which function and which area. Then it initiates the objects, and also initializes the assets such as screenshot by loading the files for template matching from Drive. Next is the function selection. If it is mining, then it asks the user to select an area. After selection, it initiates the threads. If it is logging, then it asks the user to select an area and initiates the mining thread only, because it does not need the yaw pitch thread. If it is pointing test, then it also asks for an area and it initiates both the mining thread and the yaw pitch control thread. Finally, just as prevention, there is a default case which contains all the invalid choices. Next is the keyboard listener, also carried over from the farming function. Finally, after ending, it waits for the threads to join. And if the function uses the pointing thread, it waits for the pointing thread to join. And that concludes everything for this video. If you enjoyed my uploads, please like, share, comment, and consider subscribing for more content like this one. Thank you for watching.